Hi, my name is Derek Waters. I'm a systems engineer with Texas Instruments in the Power Interface Group, where we build USB Type-C and power delivery products. And today I'm going to talk to you about USB Type-C and power delivery in general, as well as mentioning some of the products that we've developed. Here is an agenda of the talk that I'm going to go through today. It's in three main categories. First, I'm going to introduce the USB Type-C and the power delivery specifications. Then I'm going to talk about some of the specific power requirements for sources and sinks that come from those specifications. And then I'm going to talk about charging applications specifically. With that introduction, let's get right into talking about USB Type-C and power delivery. This is a timeline of some of the changes that have gone on in the USB Type-C and power delivery specifications. It's kind of interesting if you look at the history of it. There was a version called PD 1.0 which used the VBus wire, or the power wire in the cable, to send messages back and forth. Because it was riding on the power wire, it had to use FSK modulation to send the messages back and forth. But with the advent of Type-C, which created a new connector and a new cable, a wire was added, which is the CC, or the configuration channel wire, was added to the cable so that the messaging can have its own wire to ride on. That way we didn't need to use FSK or high frequency messaging. Instead we can use a BMC, which is a baseband style communications, which is much simpler. So PD 1.0 never went anywhere in industry, but Type-C, which was first version 1.0, came out in July 2014. Right on the heels of that, the PD 2.0 came out, and those were co-developed very closely. Now, you can see that about every 6 months there's been an update to those two specifications as different companies built systems and different companies built silicon, and we found issues or things that could be improved. The specifications have been adjusted accordingly to incorporate those fixes as well as add new features. At the same time, the USB Type-C created a way to use alternate modes to send other kinds of data over the USB connector. So in parallel with these USB specifications, DisplayPort, MHL, Thunderbolt, and HDMI have all created alternate modes that can be used on Type-C. That just increased the adoption and the broad-based appeal of this specification. And then USB started working with IEC to develop an international standard, international version of the specification, and there were some new requirements coming back from IEC that needed to be put into USB to make it ready for that. At the same time, there's a USB authentication specification being created, and it had some special requirements that it needed from the power delivery messaging. So in order to avoid interrupting all the companies who were building and ramping with PD 2.0 systems in the 2015 and 2016 and even into the 2017 timeframe, it was decided to create a PD 3.0 system that would incorporate those new features from IEC and USB authentication without disrupting the PD 2.0 rollout. So that's kind of one of the big reasons the PD 3.0 came about. You can see now that the version 1.2 of PD 2.0 is the final version. There will be no more updates there. Going forward, all corrections, improvements, or anything like that will be in the PD 3.0 spec. The PD 2.0 has been proven very reliable in the market, and there should not be any reason that it needs to be fixed. The USB has also started certifying chargers. So you see an example of the logo here for a certified charger. So after the maturation of the PD and Type-C specifications, there was a creation of a logo certification program for USB chargers. And as I mentioned, PD 3.0 is continuing to add new features. One of the latest new features that's added is a programmable power supply, or PPS as it's known, which was added in version 1.1 in 2017. Now let's look at the Type-C connector. So this is the mechanical, and we'll also talk about the electrical definition of the receptacle itself. You can see there's a picture of what the receptacle looks like on the top right corner. Well, the first thing to note is that there are 24 connections or 24 contacts in this receptacle. There's 4 ground connections and 4 V-bus connections, so that it can carry a lot of current. These need to be able to carry up to 5 amps through this connector. So that's why you have so many V-bus and ground connections. The next thing is there's 8 high-speed data signals, the TX1, TX2, RX1, RX2. So those carry USB superspeed data, but they also are used for alternate modes often, like DisplayPort alternate mode uses those, for example. And then, of course, we have the USB 2 data lines for backwards compatibility or for USB 2.0 data. Those are in the center of the connector. And then we have the SBU pins, which are sideband use, which also are used for alternate modes primarily. For example, the aux channel and DisplayPort. And the real key to this whole system is the CC1 and CC2 pins. Those are what is called the configuration channel. That's how it's detected that there's a cable attached. It's how we detect the orientation, how we do the roll detection in the current modes. And one of those is going to become VCON once it's connected to the cable. But I'm going to talk in more detail about the configuration channel and all that it's used for in the following slides. So here again, I'm showing the receptacle on the top with all the contacts it has, but then also the picture of the plug, which is going to be mated to the receptacle and its contacts. So the first thing I want to point out is there's not 2 pairs of D plus D minus. Some of those contacts are missing. So that means there's actually only 1 pair going through the cable for the D plus D minus. And again, there's 1 CC here, which is going to be a wire that goes from end to end in the cable, and then there's a VCON contact, which usually is just a contact locally to the end of the plug to power some electronics, like a signal redriver. In a system with it, which has a receptacle on it, one thing that can be done is you can short the D1 plus and the D2 plus, and then you can short the D2 minus and D1 minus. So that way, regardless of the orientation of the plug, how it's inserted into the receptacle, you still have your USB 2.0 data. And then notice again the symmetry of the contacts here. So the CC1 is diagonal and opposite of CC2. And the RX pair is diagonal and opposite of the other RX pair. So you can see that if the plug's inserted right side up or upside down, they'll still be in alignment. All the VBus and ground pins will align. And then based upon how the system detects CC1 or CC2, sees the CC pin, that will determine the orientation of the plug. So because of that flippability that's inherent in Type-C, you're going to need to have a MUX if you're doing a USB 3.1 system. But again, because you have the symmetry with the D plus, D minus, with all the contacts, if you're just doing a simple USB 2.0 system, there's no need for a MUX. So I want to illustrate the reason for the MUX and how it kind of works in the system. I think it's easier to see that in a picture here. So what I've drawn is just the data contacts in the receptacle and plug through the cable in an end-to-end system. I'm not showing the VBus, the power, in this illustration. So first, if we look at the receptacle on the left-hand side, you can see that it has an RP pull-up on the CC1 and on the CC2 pin. So this would be the source side of a connection. So as long as there's nothing plugged in, it's going to see a high voltage on the CC1 and CC2 pins. But once you connect the cable and then you connect a sink on the other side of the cable, you're going to see that the sink has the RD pulled down on CC1 and CC2. So the source will see, in this example, CC1 has been connected to CC, follow the green dotted line, and that RD pull down is going to cause the voltage seen at this pin on the source to go down. That way the source knows, first of all, that something has been attached, a sink, and it's going to know which of the CC1, CC2 pins is connected through to the sink. And that's how it knows which way to drive its mux. In this case, it's driving it up through the normal path. At the same time, if this is a system that uses the superspeed lanes, then the source has to provide 5 volts on the other CC2 pin, so it will power VCON, or the voltage for the connector. And you might be wondering, well, why is that necessary? Why is 5 volts necessary to be applied to the cable? We didn't need that in the old A to B cables. The reason is USB Type-C and power delivery allows the voltage going through the cable to be raised all the way up to 20 volts. So the electronics in the cable can't power from VBus directly because they would have to power from much higher voltage, which makes them more expensive. So instead, the solution that USB came up with is to require the host that's using the superspeed lanes to provide a 5 volt supply. That way you can still have low voltage electronics in the cable that are powered. Okay, we talk about the sink side now. It's been applying the pull down on both CC1 and CC2, and before something's connected, it sees 0 volts there. But now, after it's been connected to the source through the green dotted line, it sees the voltage on the CC1 pin go up. So it knows to expect the orientation to be such that it needs to set the mux as shown here, so the data flows through. If we look at the same picture, but now let's look at it flipped. Okay, so now the source is applying its RP pull-up. It's looking at it, sees the CC2 pin get pulled down. So now it knows that it's got to change its mux so the data gets routed towards the bottom. And then it'll go back through the cable. The sink sees it coming out the same way in this example. But you can see, based on how you flip the cable, there's 4 different possibilities here. And both the source and the sink both need a mux to be able to route the signals correctly in the end. So let's look at the cross-section of that USB cable. Again, this is the USB Type-C cable with a C plug on both ends. It can be plugged in either way into systems, and it'll work fine both ways because of that way the configuration channel works, as I described. Well, the first thing, if you were paying attention, that you may have had a question about was, why do we have 8 wires in the USB Type-C cable when, as illustrated in the previous slide, we're only using 4 of those at a time? Well, the first response to that is that they're reserved for future use. In fact, USB 3.2, which has recently come out, uses all 8 of the wires to get to a faster data rate on USB. But even today, some of the alternate modes use all of the wires in the cable to display video and to get faster data rates. So just because they're not used by USB 3.1 doesn't mean they're never used. Just want to make sure that that was clear. But you can see in the cross section kind of where the wires are. The superspeed wires are around the outside layer, and then there's the power wire along with them, and then the rest of the wires, the smaller wires, are bundled together in the center. Let's talk now about how to convert traditional USB systems into USB Type-C systems. And we'll start with the simplest USB 2.0 USB Type-B system. This is a USB device, and if I want to convert it, you can see going from the left-hand side to the right-hand side, obviously you have to change to a Type-C connector, but besides that, the only other thing you really have to do is put 2 RD pull-down resistors on the CC1, CC2 pins, and short the D1 plus to the D2 plus and the D1 minus to the D2 minus, as mentioned earlier. Then it looks just like a system you have today. If we move to the USB the USB 3.1 system, again with a USB Type-B connector, it gets a little bit more complicated. In the 2.0 system I showed on the previous slide, it was going to be limited in power because it didn't have any Type-C controller to recognize how much power the source is advertising. But in the USB 2.0 system, it may be a safe assumption that the USB default current is sufficient. But here in this slide, I'm showing converting a USB 3.1 system. So let's assume here that we want to take advantage of being able to sync more power from Type-C. Well, we can do that without any extra cost. So what we do in this system is we have to know the polarity of the plug. So we have to do the appropriate logic on the CC1 and CC2 pins to determine the polarity so we can flip the mux in the appropriate orientation. And TI has a part that does that in an integrated fashion, the part shown here. Well, the advantage here, as I mentioned, is that now with this Type-C controller in place, you can recognize how much power the source you're connected to is providing. So you could draw up to 15 amps in this system. So now let's look on the other side on the USB Type-A system if we want to convert it to be USB Type-C system. And let's start again with the USB 2.0 system, where it's actually just a matter of replacing the USB switch. In a traditional Type-A system as shown on the left-hand side, there's a current limiting power switch, and then there's your data system. In the Type-C, it's the same way. You need a current limiting switch, and you also need the logic to control the CC1, CC2 to handle that logic appropriately. Well, TI has a part, the TPS25821, which does that for you. It's a current limiting switch combined with a Type-C logic. In this case, it's a USB 2.0 system, so we do not need to apply VCON to the connector since we're not using the super speed lanes. But if we look at a USB 3.1 system, it gets a little bit more complicated because now, not only do we replace the switch as shown here, we also have to do two other things. First, we need to apply the 5 volts to the cable through the VCON, and this USB power switch does that, the TPS25820. It will apply VCON to the appropriate CC1 or CC2 pin. But also, we need to have this mux. And this is a discrete mux which will switch in the super speed lanes in the right configuration, but it's controlled by the Type-C controller. So once the TPS25820 or Type-C controller detects the polarity of the plug, it has a signal by pulling high or low that will tell the mux which way to route the signals. So let's look again in a little bit more detail at the USB 2.0 Type-C DFP solution. At first glance, it seems like I could just use a power switch from a legacy Type-A system and just put pull-ups on the CC1 and CC2 pins. I mean, is that enough? Is that something worth exploring? Well, we'll look closer at that. But first, I just want to point out that the existing power switches today for USB Type-A, the quiescent current on those in a range of 60 microamps or so, because USB-A is a hot socket, meaning 5 volts is always turned on. Type-C, the Type-C connector is a cold socket, meaning the 5 volts is not turned on until something gets plugged in. And we leverage that fact in our parts like the TPS25810 to have the quiescent current be very low, less than 1 microamp. So that the first difference I want to highlight is that quiescent current is dramatically different between a legacy power switch and the TI's Type-C integrated solutions. So as I mentioned, the Type-C is a cold socket by design. So if you look on the right hand side, that means if I have a controller and switch here that does Type-C correctly, even if my power supply is putting out 5.5 volts, it'll be 0 volts at the connector until something's plugged in. Or if you did try to do the simplified system as shown in the previous slide, to try to use the RP pull-up to the V-bus, then you're going to have a hot socket. 5.5 volts will be there at all the times. So that is not compliant with USB Type-C specification. So even though I'm recording this, I can sort of sense there's some skepticism out there. Why do I really have to keep Type-C as a cold socket? Is that really necessary, or is that just something that Type-C has done in an arbitrary fashion? Well, as you'll see here, having Type-C as a hot socket does create a dangerous situation. Let's look at a situation where you're connecting a Type-C source to a legacy Type A laptop, for example, or it could be any Type A legacy system, but if you look at it, the legacy system has a hot socket, right? So it's going to have its 5-volt source, and it's going to be always providing that out. And the key part of this is the Type A to Type C cable and what it looks like inside. On the CC wire of the Type C end of that cable, there is a resistive pull-up to the VBus wire. Of course, there's some resistance in the VBus and ground wires of the cable. And then that's connected to this receptacle with a hot 5 volts. So now you've got 5 volts sitting on the end of the Type C cable, and the CC line is being pulled up to it. Now if I take and plug that into the Type C, what's going to happen? Well, if I have this non-compliant Type C source, it's also going to have a hot VBus here, which might be up to 5.5 volts. And now you can see that if I take the 5 volts from the A system and have 5.5 volts from the Type C system, and I plug those together, now I have two sources trying to drive the cable. Well, a lot of times these legacy A systems don't have reverse current protection. So what's going to happen is that if the Type C source has a higher voltage, it's going to be trying to drive current into the legacy system because it has the highest voltage. And that means like the internal rail on a laptop or some other legacy A system, the voltage on that internal rail might be increased to whatever the voltage is of the Type C source. And that could damage some of those devices. So that's why I call it a dangerous situation. It's dangerous for the legacy A system. But now if we look at the same situation with a compliant Type C source, you'll see that it's completely safe. Because now we have a controller and a switch, which is keeping a cold socket on the Type C end. So even though you have a Type A being plugged in, which has 5 volts, it's okay because there's no voltage on the Type C side. So there's no current that is being driven into the laptop. There's actually one other thing worth mentioning here in this slide, and that's how much capacitance is allowed on a VBus of a Type C system. If we look at a legacy Type A, which is always going to be a source, then it's very common to see 120 microvolts on VBus directly. Well, in a Type C system, we can't have that much capacitance. The reason is because of the same scenario where a Type A can be plugged directly into a Type C. Remember, this Type A port was designed to be plugged into Type B ports. And if you look at the rules for Type B, they're only allowed to have 10 microfarads on the capacitance. 10 microfarads of capacitance on the VBus. Well, even though I'd like to put more capacitance on my VBus and my Type C, I can't exceed what's allowed for Type B because this Type C connector could be plugged into a Type A connector. And since Type A is only expecting a maximum of 10 microfarads, then it's been designed for that amount of inrush current and no more. And a lot of the Type A systems have slow current limiting switches, and they can't handle more capacitance than that. If they were to see a large capacitance, it could cause their internal rail to crash. So that's why a Type C system has to meet the same VBus capacitance requirements as Type B. So you see in the USB Type C specification, there is a table which clearly shows that the Type C receptacle cannot have more than 10 microfarads of capacitance. So let's go back and look at that discrete solution again. Now that we see that we can't have a hot VBus in a Type C solution, now the discrete solution gets a little more complicated. Now we need to have this logic, just like some example logic is shown here, of what it would take to detect that sink has been plugged in, to depound it appropriately, and to only turn on this power switch once a sink has been connected. So that would implement the cold socket part of this requirement. So you can see there's quite a few little discrete components required to achieve that. And in some cases, the power switches don't discharge VBus, which we need to do. So you may have to have a switch like this to discharge VBus in the end. Well, now the comparison's obvious. I wouldn't do all of this. The amount of engineering and design required there is significantly higher than just taking an integrated solution like this one from TI and putting it on your board. Okay, so now I want to talk about one of the new things in Type-C, a dual role port. Well, a dual role port means that it can be a source or a sink, depending on the scenario and the usage case. Well, we've seen that sinks apply an RD pull down and sources apply an RP pull up, so they can detect when they're connected to each other. But what about a dual role port? If it can be a source and a sink, well, how does it know what it is in a situation? Well, I have an illustration here that'll show you kind of how that works. So let's look at a laptop, classic example of a dual role port, because it wants to sink to charge its battery, and it wants to source to connect to a hard drive or a mouse or many other things. Well, when it's in the source mode, the laptop is going to be applying RP pull-ups, as shown here. And when it's in a sink mode, it's going to be applying the RD pull-downs. So when nothing's connected, it's going to be toggling back and forth from pulling up and pulling down, because it doesn't know what it's going to get connected to. It could get connected to a source or a sink. Well, let's walk through what happens when the laptop is connected to, let's say, a charger, which is always a source. In the end, you want the charger to be the one providing voltage and power to the laptop. Okay, first, the laptop is again toggling from pulling up, pulling down, pulling up, pulling down. And the charger is just always pulling up. So if I take and put a cable in between there, again, my laptop, it might be pulling up, so at the time where they're both pulling up with RPs, they don't see each other. But remember, the laptop is toggling, so very soon after, the laptop is going to toggle to pulling the RD pull down. And at that moment, the charger is going to see the voltage on its CC1 pin go down, and it knows something got plugged in. And the laptop sees the voltage on its CC1 pin go up, so it knows something got plugged in, so that it stops toggling. And then the charger will validate the connection and provide 5 volts on VBus. Well, let's look at the other scenario where a laptop, let's say, gets plugged into a phone, where the phone wants to be the sink and the laptop wants to be the source. Again, the laptop is sitting here toggling back and forth, pulling up and pulling down, and then it's plugged into a phone, which is always pulling down, let's say, in this situation. So if it's plugged in at the right moment, the laptop and the phone are both pulling down, so they're both seeing 0 volts on their CC pins. But then shortly after, the laptop will toggle and pull up on the CC pin, but it will see that the voltage on the CC1 pin in this example doesn't come as high as on the CC2 pin, so it will recognize that there is a sink connected. And the phone will see that the voltage goes up on its CC1 pin, and it'll know that a source got connected. So the laptop stops toggling and provides 5 volts to the sink. At that point, the laptop might change its RP pull-up to a different strength, so it could advertise 3 amps or 1.5 amps or something lower. And at that point, if they both support USB power delivery, they could start sending messages on the CC wire to communicate to one another to do various things. But it all starts with this initial connection from a DRP laptop to a sync-only phone. So another great thing about USB Type-C is it creates a common connector that can be used for many applications. And it provides a legitimate path towards a universal charger because it is so broad in its applicability. Today there's many different things under the USB Type-C umbrella: laptops, docking stations, monitors, tablets, and that can even expand more in the future. If you look at in the past, what's been the case is lots of computers have their own special barrel jack adapter. And so if you look in some an IT department which has to service all these kinds of laptops that may come in, they'll have a whole wall dedicated to different kinds of chargers needed for that. So that creates a lot of e-waste, as you can imagine, as people move from one laptop to another and they need to throw away their old power brick. That's why USB and IC are working together to try to create a ecosystem that can make chargers more reusable and reduce e-waste in the end. So USB power delivery over USB Type-C. Let's open that door now. Well, you can have a system with just USB Type-C. it doesn't have to have USB power delivery with it. But what USB power delivery does, first of all, as implied by the name, is it allows you to increase the amount of power. So with USB 2.0 and 3.1, you can get 500 milliamps to 900 milliamps. BC 1.2 allows you to get up to 1.5 amps. There are some proprietary techniques that can go higher power. But now if we move into Type-C, first of all, you can do the same as BC 1.2 with 1.5 amps, but then you can go all the way up to 15 watts, so it doubles the amount of power from USB before. And but that's as far as you can go with just Type-C. But if you use USB power delivery, you can get a huge jump all the way up to 100 watts because you can increase the voltage, first of all, up to 20 volts, and you can increase the current up to 5 amps. So you can see that the number of applications that can be addressed by the amount of power in USB is going to be extended. Instead of being restricted to phones, cameras, smaller things, now you can power laptops. Monitors can provide power to laptops. There's a lot of scenarios that are possible now. And one thing worth pointing out is that USB Type-C doesn't allow proprietary modes over the D+D- anymore for negotiating voltage. So that's something to keep in mind going forward. So what are the other features in USB power delivery? We know that it enables higher voltage and higher power, but it also does other things. First, it can allow the port to negotiate which side is the downward facing port and which side is the upward facing port. So you can now have an upward facing port which is providing power, which creates some new use cases. And this is kind of built in to the USB negotiations. The USB power delivery negotiations. It has efficient power management mechanisms built in to allow managing power across multiple peripherals. It has messaging, which allows for determining the capabilities of a connected device. It has, as kind of discussed in some of the things before, its coexistence with legacy USB products is part of the standard from the beginning, so it will be completely legacy compatible if you have the right A to C or B to C cable. And lastly, it enables alternate modes. Now, some of these things are not related to power directly, but they still require USB PD. The reason being is the USB PD creates a side channel to allow things like alternate modes to be negotiated. So the way the flow happens is first there will be a negotiation based on the Type-C and the RP, how much current's available. Then there'll be a negotiation on power delivery over the CC wire, and that negotiation could cause the voltage to go from 5 volts to 20 volts or whatever else it might be. It might stay at 5 volts. But after you've gotten into that contract and the source and sink have agreed on the power being delivered, then they can move on and discuss alternate modes. Do they want to do DisplayPort or Thunderbolt or some other alternate mode? Okay, so let's summarize this first section of the talk. So why convert to Type-C? I tried to cover some of the features of it to give you a flavor of why you want to convert to Type-C. The new and smaller connector, which is conveniently flippable, of course. We talked about the implication that has on the system with the MUX. I mentioned how, especially on the source side, you can reduce quiescent current significantly. Showed an example of from TI legacy Type A power switches to Type C power switches, and it goes from 60 microamps to less than 1 microamp quiescent current. The other thing with Type C is that you can provide or consume more power. And then on the power delivery side, you can provide or consume even more power, first of all, by increasing voltage and current. But also you can configure those alternate modes we discussed. And that has one great potential effect, which is to consolidate connectors on an electronic device, which can really help with the form factor that everyone strives for these days. So those are some good things to think about as you look at converting or just understanding what Type-C is. Alright, now let's move on and look at the power requirements for source and sink. In order to look at the requirements from USB power delivery on a system, I've chosen a power bank example. PCs were the first to adopt Type-C because, in large part due to the port consolidation it allowed to save cost. Well, in a power bank is another product where that really makes sense, because if you think about it, A plus B equals C in the USB system. For a power bank, instead of having a USB B port to charge the battery and then a USB A port to charge your phone when it gets connected to it, now you can have just the Type-C port. When the power bank's empty, you charge it up to the Type-C port. When you're ready to charge your phone with it, you connect it to the Type-C port. So it's a really good system example, I think, for illustrating a sourcing and sinking requirements. So the system that I'm going to talk about is based on a reference design that TI has done, and it actually has a Type-C port and a Type-A port. Of course, the Type-A port is optional, but there's still a lot of legacy devices out there that may want to use A to B charging. So I won't discuss that much, but it's there on the design. This reference design leverages the BQ25703A battery charger and a USB PD controller from TI. First of all, let's look at a model of the source and sink systems. Below, you see on the source side with just kind of what it would look like from a power perspective, not showing any data lines or anything, and then on the sink side with a cable in between. So let's talk about that. First thing is note the capacitive limits. The source is almost certainly going to have much more than 10 microfarads on its bulk capacitance, but that's hidden behind these power switches. So at the connector, make sure you have less than 10 microfarads so that you can have legacy compatibility. On the sink side, again, it's very similar. It needs to have less than 10 microfarads at the connector, and then it might have more capacitance on the load, but the total should not be more than 100 microfarads. On the source side, let's look at the Q1 switch. The reason it's required in many systems is because you need to have a cold socket. So that's the way, in this illustration, VBus can be turned off by turning the Q1 switch off. The Q2 system is there to prevent inrush current into the bulk capacitance here. Again, that's for legacy compatibility. And then I'm showing a sense resistor here just to illustrate that the source has some way to either limit current or do an overcurrent protection in case there's a short on the VBus. If you're moving over to the sink side, Q3, again, that's to limit the inrush current into the big bulk capacitance, but it also enables overvoltage protection and removing the load from the VBus pin if required. And finally, Q4 is needed in subsystems to avoid driving VBus. So, for example, if the capacitance got charged up to 20 volts while it was connected to a source, if the source gets unplugged, but for some reason the load was not draining that capacitance, we need to make sure that that 20 volts does not sit on VBus after the cable is removed. So that can be achieved with a switch like Q4. Well, as I mentioned, the power bank, it might be a source or a sink. And so it has a back-to-back FETs in this application. You can see the PD power controller that's used in this reference design has a back-to-back FETs integrated inside. And that allows the system to be like the model in the previous slide. So it can isolate the bulk capacitance, it can turn off the load as required. Let's get down to some nitty-gritty details here. Let's look at the voltage levels in the system when it's in a sink mode. According to the USB PD specifications, the source has to output at least 4.75 volts at its receptacle on VBus. That current is going to go through a resistance on the ground wire and on the VBus wire in the cable. And if the sink is pulling 3 amps, it may see as little as 4 volts at its connector. And then inside the sink, there are other resistances. There's a resistance due to the connection, the mating of the plug and the receptacle. That is shown here. There's the resistance of the back-to-back FETs that we showed. And then there's other resistances in the system, such as the traces and the PCB, and there may be other FETs depending on the type of load you have. So in the end, we need to make sure that the load sees at least 3.5 volts, because in this example, that's the battery charger requires that much voltage in order to operate. So we look at these different resistances on the sink side. The FETs could be 46 milliohms. The mating resistance with the plug and the receptacle may be 40 milliohms. So that means that we need to make sure that all the other resistances are less than 80 milliohms. And that way we'll make sure that the voltage seen at the load is high enough. Now let's look at the same type of analysis when the system's in the source mode. Here we're going to have to balance the accuracy of the source voltage and its nominal level, balance that with minimizing the resistance in the path to meet the requirement. So the source has to be able to output between 4.75 volts and 5.5 volts for all loads at its receptacle. So if we assume that the source is a plus or minus 3% accuracy, assume we're sourcing 3 amps, and let's just take as an example of something that doesn't work. Let's say that the total resistance in the system is 166 milliohms. Well, that means in order to make sure that V source is greater than 4.75 volts, then my source voltage has to be 5.41 volts. But in order to make sure that my voltage at my connector does not exceed 5.5 volts, that means that the V source needs to be less than 5.34. So obviously, this is not going to work. The light load and the heavy load scenarios cannot be both supported with this. So you have to manage those resistances appropriately. So if we take those two scenarios together, the sinking and the sourcing scenario, first, to meet the requirements on the sink side, I just need to make sure the system resistance is less than 166 milliohms. That's no problem. On the source side, first I need to make sure that the system resistance is less than 110 milliohms, and if I do that, then I need to set my nominal voltage output on the battery charger to 5.25 volts instead of the 5 volts, which you might do when you first look at it. That'll help meet the light load and the heavy load requirements. Now, one thing I wanted to sort of point out as a side note is the USB power delivery does allow something called a peak current mode. In that mode, it allows a sink to draw up to 6 amps for about 10 milliseconds at the max, and then it has to be in a duty cycled fashion, so on average it's only drawing 3 amps, but it allows those 10 millisecond pulses up to 6 amps. Well, obviously if you're supplying 6 amps, all the IR drops that we looked at are going to double, so you have to redo this analysis to make sure you can still meet all those requirements. Okay, now besides just voltage and power requirements, there are a lot of timing requirements in USB Type-C. So one thing that happens is whenever a source and sink are negotiating the power contract. Okay, so the way it works in USB power delivery is the source, he first just lays out before the sink all the things it can do, how much power it can provide, which voltages it can provide. I like to make an analogy that it's a buffet. The source is laying out the buffet for the sink to choose what it wants. So the source can say, at 5 volts I provide 3 amps, at 9 volts I provide 3 amps, 15 volts I can do 3 amps, or at 20 volts I can do 2 amps. Okay, so it lays out before the sink what the options are. And the sink, depending on what it needs, it might pick the highest voltage, or it might pick some lower voltage at a higher current. That's really a decision for the policy manager on the sink side. So once the source sends what's called a source capabilities message, which is the buffet menu, Then the sink sends a request message which specifies which of those options it wants. The source evaluates that request. Then it will send an accept message if it's able to meet the requirements that the sink asks for. After it sends that accept message, this is where the timing comes in. The source waits for 25 milliseconds before it actually starts to transition the voltage. That means the sink, it needs to make sure it's not drawing more than 2.5 watts during the voltage transition. So it has 15 milliseconds to reduce its load. So you can see on the bottom here, the sinking, the amount of current being sunk by the sink is reduced here from whatever it was before down to 2.5 watts. And then after that's happened, the source completes the 25 millisecond wait and it will start increasing the voltage. So there'll be some extra inrush current into the sink bulk capacitance during that time, but it's still a pretty low load here. Once the voltage has completely transitioned, then the source sends a power supply ready message. Upon reception of that message, the sink sees that, and only then does it increase its load. Okay, so after the voltage has reached its final point, the sink may still be sitting with a 2.5 watt load until it receives this message from the power supply saying that it's ready to supply the full current agreed to. In this reference design we're discussing, the PD controller handles those timing requirements. For example, when the power bank is in the sinking mode, the PD controller will receive the accept message from the source, and then it will tell the system to reduce load to less than 2.5 watts. It does that by writing a register over I2C in the battery charger. And then the battery charger will reduce the current being drawn from the source. All of the firmware inside the USB PD controller ensures that this timing is met. Another requirement from USB power delivery is the voltage overshoot, undershoot, and the transition characteristics. So we already saw that the sink can't draw more than 2.5 watts during the transition. But what about on the source side? What are its requirements during the transition? Well, first of all, the source is allowed to have a 0.5 volt dip as it starts the transition. It may be switching from one path to another, maybe switching FETs. Then it's allowed to have a little bit of a dip. The slew rate during the transition cannot be faster than 30 millivolts per microsecond. And the overshoot is not allowed to be more than 0.5 volts above the maximum tolerance range. And it could have overshoot and then come back undershoot depending on the regulation. But again, it's a 0.5 volts on the overshoot and on the undershoot. After 275 milliseconds, the tolerance on the final voltage is a little bit tighter. It's plus or minus 5%. So you can't have the 0.5 volts over and undershoots anymore after that. The requirements on the negative voltage transitions are very similar. That the source can't discharge too fast, and it has the same type of over-undershoot values that it needs to meet. Another set of requirements for the source is how does it handle load transients on VBus. Well, when there's a load transient, it could be positive or negative, the source voltage tolerance is expanded by that 0.5 volts again. So that gives a little bit more leeway in adjusting to that load step. So for up to 5 milliseconds, it has an extra 0.5 volts in its regulation. And again, that's for a positive load step or a negative load step. Another interesting thing is on the sink side, the load step rate is limited to plus or minus 150 milliamps per microsecond. So the sink should do its load steps in a controlled manner to obey that requirement to make sure the source is able to maintain regulation through any load step that it sees. Now let's go and look a little bit more specifically at the charging applications, which are source-only applications. Here I'm showing a simplified diagram of an AC/DC source. This could be in a wall outlet, or it could be in a power brick, but the basic system looks very similar. First of all, you have a flyback, which needs to be able to do multiple voltages if you're doing high power. So in this example, I'm showing that it does 5 volts, 9 volts, or 15 volts coming out because it's a 45 watt power supply. The PD controller, it handles all the messaging, handshaking, so it sends source capabilities, evaluates requests from the sink, and then communicates with the sink that it's accepted the request, and lets the sink know when it can start drawing power with a PS ready message. So that handles the timing and everything involved in that. But it also controls the power supply to select the voltage at the proper time. And finally, it controls the back-to-back FETs shown here. So in a receptacle application, we do need back-to-back FETs here because this AC/DC flyback is going to have a huge bulk capacitance here that needs to be isolated. We do have TI designs that implement these AC/DC systems, and the numbers are shown here, which you can find on ti.com. The PD controller that we've used in these designs is the TPS25740A. One thing I want to point out is, again, we used a back-to-back FET here in the receptacle design, and if you look at a captive cable design, so that means the power brick has a cable permanently attached to it and then a Type-C plug on the far end. So in that type of system, we do not need a back-to-back FET. The reason for this is that there is no cable that USB has defined where a Type-C plug can be connected to a legacy A receptacle. Remember, the whole reason for that FET was to limit inrush capacitance from a legacy A port. Since a legacy A port cannot be connected to this captive cable source, there's no need to have that FET. So the only FET that I'm showing here is the one that allows us to get to a cold socket. Because even though we have a captive cable, we still do need to be able to get to 0 volts on VBus per USB PD specifications. That's because when the fault happens, there's something called a hard reset, and the source during a hard reset has to drive the VBus down below 0.8 volts. That way the sink will get reset and the whole negotiations and everything can start from scratch, start clean. If the source doesn't take VBus down during a hard reset, there's no way to ensure that the sink actually gets reset and everything starts from scratch. So some fault that has happened might persist. So we still do need to be able to get to the cold socket here, and that's why this FET is shown in this example. This shows a little bit more detailed schematic of what that system might look like. This is, again, the captive cable example. So there's only one FET shown here, and there's a Type-C plug that it's connecting to. Here you have AC/DC flyback shown, and what I wanted to highlight on this slide was how the PD controller selects the voltage. So you can see there's a resistor divider here from VBus, or from the output of the flyback, and that resistor divider is used to drive the optocoupler, so you have a closed loop regulation of the voltage. So by default, whenever CTL1 and CTL2 are open drain, these two resistors are not a part of the resistor divider. So when that happens, you have 5 volts from the output. During negotiations, if it needs to increase the voltage, then the PD controller will pull down on the CTL1 or CTL2 pin, and that will change the resistor divider such that the output voltage is increased as needed or as requested by the sink. So as I was just saying, upon a hard reset, which happens from a fault, or when you unplug, the source does need to get VBus down to 0. But the slew requirements don't have to be obeyed in that situation. So it can just turn off as fast as possible. And that means that the source is going to need to discharge its bulk capacitance in a lot of cases. And the most difficult scenario actually for discharging that capacitance is not from a hard reset, but if let's say the source is providing 20 volts, but the sink decides it wants to only go to 5 volts. So the sink will send a request saying, please give me 5 volts. But the source cannot depend upon the sink drawing any load during that time. So the source needs to be able to discharge that capacitance on its own. Now, in some power supplies, that's not a problem. There's a inherent discharge capability in the power supply itself. But in some cases, that's the PD controller needs to be able to discharge that voltage or that capacitance down. And it needs to do that within 275 milliseconds. So you can see in the chart here, this is what's shown for, it kind of covers both the hard reset and just discharging to a 5.5 volt case. If I'm discharging from 20 volts down to 5.5 volts, I have to do it in 275 milliseconds. That's the same for hard reset or for a normal negotiation. For a hard reset, the shaded region comes into play. I need to get from the 5.5 volts down to 0.8 volts, and so the total time there needs to be less than 650 milliseconds. And then the source has to hold the voltage low for about a second to complete the hard reset and ensure the sink has reset itself. And then it'll turn the VBus back up to 5 volts and start over again. So if we go back to our schematic view, this PD controller does have a way to discharge the voltage down. In this case, there's no inherent load to discharge this big capacitance, which may be huge. It could be up to millifarad. So this PD controller has a dedicated discharge pin, and that's the discharge path for that capacitance. But because of the amount of energy that needs to be dissipated, there's an external resistor placed in series with that discharge pin. So that resistor is what absorbs most of the energy during discharge. So let's look at the typical behavior upon attachment of a sink to a source. So on the chart shown here in the bottom right, it shows the CC1 and the CC2 voltages and the VBus voltage. So initially, VBus is at 0 volts, and the CC1 and CC2 pins are being pulled up. The first thing that happens is there is a cable attached. So you see that CC2 gets pulled down to like 0.4 volts. That means that the RD pull down on the sink has been detected. You can see that the other CC pin does drop a little bit, but that's just because the PD controller, after it saw CC2 go low, it switched to a different RP pull-up, but it's still very high. This is not low enough to be a sink. You can see there's a big gap between the two. The next thing that happens is the source has finished confirming that there's a valid sink attach. According to Type-C specifications, that needs to be between 100 and 200 milliseconds. So that's a debounce that is inherent in all Type-C controllers. So after that debounce time, you can see that first the VBus is turned on, but also the PD controller in this scenario applied VCON to the CC1 pin. So you can see the voltage on VCON goes up and VBus has gone up. The next thing that happens is that the Type-C PD controller changes its advertisement. So the 0.4 volts here is a default USB current. And then at T3, you can see some noise here in the signal. That's actually the USB PD communications. The source here is telling the sink which voltages it supports. But in case it's connected to a sink that doesn't understand USB PD, it does switch the RP pull-up strength. In this case, it's advertising 3 amps with the RP pull-up. However, as you can see through the noise kind of down here in this black line signal, the sink did reply and it did respond to the source capabilities, and it did ask for another voltage. So the source saw the request, accepts the request, and then it increases the voltage on VBus. In this case, it went up to 12 volts. So at T4, the sink has got the voltage you ask for, and the source will soon after send the PS ready, and the sink can start drawing current. Now let's talk about some dual port options for chargers. The previous slides looked at the single port version, but USB Power Delivery has some interesting tools and mechanisms which allow it to be, it creates some very interesting use cases for a dual port charger. First of all, there are two categories that USB Type-C defines for multi-port chargers. And the first one is an assured capacity charger. So that means once a sink is attached to a port on a multi-port charger and it's agreed to a power contract of a certain number of watts or certain voltage, that contract would never be removed by the sink. So the sink, by the source. So a sink is assured that the source will not change the contract. On a shared capacity charger, there may be a limited amount of power that needs to be shared across multiple ports. So in that type of multi-port charger, the charger can decide to change the contract at any time depending upon what's happening in its system. So the sink is not assured that the PD contract won't be changed. So that's really the two categories: an assured capacity charger and a shared capacity charger. So I'm showing two kind of examples of how that might play out in an actual multi-port charger. On the left-hand side, each port is able to do up to 45 watts. So if the sink gets plugged in, there's 45 watts that it can be assured that it can have access to. That means the flyback needs to be capable of doing 90 watts because there might be two sinks plugged in at the same time, and you're assuring 45 watts to both sinks. So obviously the flyback has to be twice the power on each port. If you contrast that with a shared capacity charger, here we can offer 45 watts to a single port if the other port is empty. Okay, but that allows us a great advantage of having a 45 watt flyback. Obviously a 45 watt flyback is much smaller and less expensive than a 90 watt flyback. So one detail in the diagram you may notice is that there is a connection between the two PD controllers. That allows them to cooperate with one another to know how much power to advertise. In this shared capacity charger, as long as one port is attached and one port is empty, the attached port will offer the full 45 watts. But when a second sink is attached on the second port, then the first port will reduce by half how much power it's advertising to the sink. And then both ports will advertise half the power, or 22.5 watts. Okay, this is a third option for a multi-port charger, or in this specifically here, it's a dual port charger. The right-hand side shows the same shared capacity charger as the previous slide. The left-hand side shows a different architecture, a different way to achieve this. Here, I mean, obviously, the very first thing you see is there's no DC-DC converter here. So on the previous solutions, we needed each port to be able to provide a different voltage at the same time, because the sink attached on port 1 might want 5 volts, a sink attached on port 2 might want 15 volts. So you need a DC-DC buck on both ports so that you can manage that. In this system, we're making some compromises in order to simplify the power supply. So we've removed the DC-DC converters, and we have a single voltage output from the flyback. In this case, the voltage could be 5 volts or 9 volts, depending on what happens. So if there's only one sink attached on port 1, so port 2 is empty, the PD controller will offer 5 volts and 9 volts at 3 amps each. So it's offering a total of 27 watts to the sink that gets attached. So many sinks would be able to benefit from the 9 volt 3 amps to charge their battery faster than they could at 5 volt 3 amps. But when the second port is connected to a second sink, so now both ports are connected, Again, the two PD controllers cooperate with one another, and they advertise only 5 volts. So the port that was delivering 9 volts, it will tell the flyback to reduce its voltage to 5 volts through the CTL2 pin, and then both ports will be delivering 5 volts to 3 amps for a total of 30 watts. So in this case, the flyback only needs to be a 30 watt capable flyback, and you get a much simpler system. You improve efficiency and you reduce the BOM cost with this approach. So in summary, this talk has covered a lot of ground. First, we've talked about USB Type-C and USB power delivery and what they are, and Type-C had a big effect on USB power delivery and moving it from 1.0 to 2.0, and then now it's at 3.0. But there's significant market traction in the PC space in 2017, and strong growth is expected going forward from here. And as the PC space and more phones start to adopt Type-C, all the ecosystem around those devices are expected to start adopting Type-C. So it's going to be exciting to see what happens there in the market. We also covered a lot of specific system details that need to be taken care of if you're looking at a USB Type-C PD system. Hopefully that'll give you some idea on where to start as you look at your system. And also, we talked about a lot of the options and architectures that are available for chargers. And that just gives you a flavor of the possibilities that are out there. And we talked about chargers, but for dual row ports and for sinks, there are similar decisions that need to be made. So hopefully this will give you also a flavor of the kinds of things that are possible that you can consider for your system. Thank you.